It's 4 in the morning. Aarhus Container Terminal. On the bridge of a Triple-E container ship, one man stares at a screen full of rectangles. 18,000 of them. Some weigh more than your car. Get the arrangement wrong, and this ship doesn't make it to its destination. In June 2013, a container ship a little smaller than this one, the MOL Comfort, snapped in half on Yemen and sank. Investigators kept coming back to one detail: the weight distribution. Right now, the chief mate is the only thing standing between a normal voyage and the next investigation. On the bridge, a red flag pops up on a screen. The software has flagged a stowage conflict. A container of lithium-ion batteries sitting 2 rows from a container of acetone. He has a seaman drag the batteries 3 rows aft. Flag clears. Next conflict. He'll do that 31 more times before this plan gets signed off. Imagine 18,000 shoeboxes. Some hit 40 tons. Some have to stay frozen for 9 days. Some cannot be near each other under any circumstances. And you have to stack them 8 high on a deck that pitches sideways. The Bay Plan is the 3-dimensional map of where every single box goes. 24 bays long, 23 rows across, 11 tiers high, 18,000 slots. The software fills every one without putting Singapore boxes under Hong Kong boxes, without parking lithium batteries next to acetone, and without bunching the heavy steel in the middle and snapping the hull. When it works, the ship leaves on time and nobody notices. When it doesn't, the investigation takes 18 months. Think of it as Tetris, where every piece weighs a different amount, has to come off in a specific order, and if you stack it wrong, the floor breaks. The chief mate signs off. Planning where the boxes go is half the problem. The other half is making sure they don't move once they're there. The shipping industry loses about 1,300 containers overboard a year on average. None of them fall off because the Bay Plan was wrong on the screen. They fall off because somebody downstairs got the next part wrong. That somebody downstairs is currently working 3 decks below the bridge with a steel rod in each hand. On the main deck, a lashing crew member drops a steel cone into the corner casting of a 24-ton container. He kicks the handle, the cone twists 90 degrees, and the box locks to the deck. Next corner, next box. 4,000 more of them before the ship leaves. That cone has a name: twist lock, the single piece of hardware that makes container shipping work. If you've ever pulled a tarp tied across the back of a pickup truck, you understand the basic problem. Now multiply it by 18,000 boxes and add 50-foot waves. A twist lock connects the corner castings of 2 stacked containers. The cone drops in, handle twists, boxes lock together. Containers stack corner to corner through these locks. They never rest on their own walls. The entire 8-high stack hangs off 12 steel cones. A standard twist lock holds 50 tons of vertical separation force and 500 tons of lateral shear. Just like Legos, except each piece weighs 24 tons, and the floor is rolling 30 degrees in a storm. After twist locks come the lashing rods, steel poles, 2 meters long, running from the deck up to the 2nd tier and bridging to the 3rd. The bottom layers carry the load while the upper boxes ride free on twist locks alone. A 30-degree roll in heavy weather implies lateral force on every stack. One failed lashing point shifts the load to the next gives, a column starts to lean, and a leaning stack collapses into the columns next to it. That's how a ship can lose 100 containers in 5 seconds. Down the next row, another crewman walks past green LED after green LED. One blinks yellow. He pulls the cable, inspects the prongs, plugs it back in. Light goes green. Onto the next stack. 600 plugs before the ship leaves the harbor, because every single one of them is a refrigeration unit that has to stay on for the next 9 days. 600 reefers, refrigerated containers, each drawing 17 to 15 kilowatts continuously. Peak load on a fully booked sailing hits about 9 megawatts of refrigeration for 9 days straight. Picture a small town's worth of refrigerators, all plugged into one ship, all running without a break. Lose power to one plug, and a shipper loses a container of frozen fish. Lose power to 30, and a shipping company starts the morning with 30 lawyers. Anything not green gets flagged to the chief's engineer's screen 4 decks down. Deeper in the hold, a container slots into the 23rd row across, the bottom outer corner, just above the bilge. On a V-shaped hull, that space wouldn't exist. The slope of the hull would have cut it off. The Triple-E's flat bottom claimed it back. The name Triple-E stands for 3 goals the design had to prove: economy of scale, energy efficiency, and environmentally improved. Maersk put it on the hull because those were the only 3 things that justified building the largest container ship on Earth. Here is what nobody mentions when they tell you the Triple-E carries 18,000 boxes. The ship right here, the Maersk, is only 3 meters shorter, and it does 2,500 fewer. The cross-section tells the story. The Triple-E is shaped like a U, where almost every container ship before it was shaped like a V. The older designs prioritize speed. A narrow V cuts through water faster. The Triple-E flattens the bottom into a wide U, keeping the same external length, but adding internal cubic meters. That shape change added 1 row of containers across the width where the Maersk carried 22. 1 extra row spanning 400 meters, 11 tiers high. 1,500 extra boxes by itself. Same shoe size, wider toe box. Way more shoe. Then they moved the bridge and accommodation block 5 bays forward and the engine room 6 bays aft, stealing space from machinery and crew and giving it back to cargo. Another 1,000 containers. 2,500 more boxes than the previous record holder. Same length of ship, same waters. They just arranged the geometry. All of this, the bay plan, the lashing, the reefers, the hull shape, only matters if something can actually move 165,000 tons of ship and cargo across an ocean. When Maersk engineers sat down to figure out how, they made a choice every marine engineering textbook says is wrong. 4 decks down, behind a soundproof door the crew has no reason to open. 2 engines the size of small houses hammer at 73 strokes a minute, slowly, about as fast as a metronome at a funeral. Behind the stern, 2 propellers spin in opposite directions, each one almost 10 meters across, together shoving 165,000 tons of ship forward at 17 knots. Here's what's strange about that. Every naval architecture textbook ever written says 1 engine is more efficient than 2. Maersk's own engineers said it for years. What none of these textbooks accounted for was the one thing Maersk was about to do that nobody else had tried. Then they built this ship with 2 engines anyway. Here's why. Up on the bridge, the throttle sits at 3/4 of where it could be. The ship making 17 knots on engines rated for 23. They could push harder. Nobody's asking them to. This isn't an engine problem, this is a deliberate choice. A container ship's fuel uses scales with the cube of its speed. Double the speed and you don't double the burn. You multiply it by 8. At 25 knots, this hull burns close to 250 tons of bunker per day. At 19 knots, the consumption drops 37%. At 17.5, it's roughly cut in half. A slower ship that uses half the fuel, even with 2 to 6 extra days per voyage, makes roughly 30% more margin per container. The competitive advantage is not speed. It's not burning fuel to push the steel any faster than it has to. But running slow only pays off if the engine is built for it. That's where the rules started to bend. Inside one of those cylinders, a piston moves on a stroke nearly 4 times as long as the bore is wide. Each cycle takes nearly a full second to complete. A car engine at idle is running 11 times faster. A conventional marine diesel runs a stroke-to-bore ratio around 3-to-1. The ultra-long stroke pushes it to 4-to-1, which gives the piston more time on every cycle, less combustion run to completion, and develops huge torque at very low RPM. Hummingbird versus elephant. The hummingbird beats its wings 80 times a second. The elephant takes 1 slow step. The elephant doesn't burn through its food. But all that low RPM efficiency only pays off if the engine can spin a propeller big enough to turn that torque into thrust. Back under the stern, those 2 propellers, 9.8 meters across, 4 blades each, shove enough water rearward to keep the ship moving at speed. The question is why there are 2 of them instead of 1. The bigger the blade, the more thrust per revolution, and the slower it can spin. Slow propeller plus slow engine equals maximum efficiency. But diameter is a hard limit. What fits under the keel? On a 400-meter ship at 16 meters of draft, the biggest a single shaft can swing tops out at around 9.6 meters, The Emma Maersk was exactly that. Maersk's engineers needed more propeller area than a single shaft could fit, so they used two shafts, two ultra-long stroke engines side by side, each driving its own 9.8-meter propeller. They broke the rule. One engine is more efficient because propeller geometry mattered more than engine count. Two smaller plants spinning two big propellers beats one bigger plant spinning a slightly smaller prop by about 10%. And they weren't done. On deck, the reefer compressors hum. On the bridge, the instruments blaze. None of that power is coming directly from the main engines. It is coming from heat that should have left the ship through the funnel. Engine exhaust runs into a boiler. Water turns to steam. Steam spins a turbine. The turbine drives a generator, and the generator feeds the ship's grid. By the time that heat finishes the relay, it has powered every reefer plug on deck, every bridge instrument, every hot water tap in the accommodation block, and the dinner service for 22 crew. 25% of the energy the funnel would have thrown away. Net fuel savings, about 9% on top of everything else. Imagine driving with a small generator hooked to your exhaust pipe that runs your radio, your headlights, and your air conditioning. You're not paying to power any of it. Final result: the ship moves a container from Shanghai to Rotterdam using about 35% less fuel per box than the ship's half its size still working the same route. Slow steaming, twin engines, waste heat recycled. That's how the ship makes money once it's at sea. Getting it there is a different problem. The one thing this ship was never built to do well: getting out of a Danish harbor. Two tugs nose against the hull, one forward, one aft. The ship doesn't accelerate, it eases, a meter at a time. A 400-meter ship doesn't really turn. It pivots, it glides. You don't drive a Triple-E out of a harbor the way you drive a Honda out of a parking spot. You ask very politely, and you give it a lot of room. The only steering surface on this ship sits back at the stern, a rudder that does almost nothing at 3 knots. The thing works when water flows fast enough over it to generate lift. At harbor speed, there's not enough flow. It's essentially a sign saying, "This way." The tugs do the actual turning. A Triple-E displaces about 165,000 tons loaded. And at harbor speeds, the rudder shifts heading by about a degree per minute. A single tug pushing sideways shifts it 5 times faster. It's like trying to steer a building. You don't. You wait for someone to come push it. The tugs disconnect. The ship clears the breakwater. Engine comes up from idle to cruise. The Triple-E's natural habitat is the Asia-Europe route via the Suez. The class is too wide for Panama by about a meter, and the draft restricts it to deep water ports. Roughly 25 facilities in the world can handle this ship fully loaded. Aarhus is one. Gothenburg is another. Most ports on Earth simply aren't built for this. You're not picking your destination. Your destination is picking you. On the bridge, the officer's finger taps a triangle on the screen. A ferry off the port bow, 18 knots, headed northwest. He calls a small course adjustment. Bring the heading 2 degrees south, push the closest point of approach to 1 kilometer. Then he goes back to his coffee. What he just did was only possible because of one system on his screen. AIS, the Automatic Identification System, is a continuous broadcast every commercial ship over a certain size must transmit, sending out position, course, speed, and ship name to every other ship within range. Line of sight reception runs 20 to 30 nautical miles. Satellites pick it up globally, air traffic control, except every aircraft is a participant. Every ship sees every other ship, all the time. Useful because a 400-meter ship cannot dodge. At cruise speed, it takes about a kilometer just to slow it down. If something appears on the scope at close range, you can't swerve. You have to have predicted it 20 minutes ago. Tugs handed off, route locked. AIS feeding the bridge in real time. From the bridge, the next 9 hours look like a quiet drive. From 4 decks down, the next 9 hours are an active vigil, because the moment this ship is at sea, the number of people running it shrinks to a number that should not be possible. 4 decks down from the bridge, behind an insulated door, the engine control room. Banks of screens, engine telemetry, fuel flow, lube oil pressure, cooling water temperature, exhaust gas temperature, every reefer plug status. One engineer on watch. Right now, on this 400-meter ship carrying 18,000 containers worth somewhere in the neighborhood of $500 million, the number of people actually monitoring all of it can fit around one dinner table. The Triple-E sails with a standard crew of 22. Legally, it can run with 13. For comparison, a cruise ship of similar physical dimensions carries around 2,300 crew, 22 people, same tonnage as the cruise ship, and most of the same problems too. An amber alert flickers on the engineer's screen. Cylinder 7, exhaust temperature creeping up, 412 degrees, then 415. No alarm in his reaction. He taps it, opens the fuel injector menu, cuts the flow on that cylinder by 2%. The number plateaus and then slides back into green. Adjustment logged, he moves on. That tiny intervention prevented something catastrophic. Fuel injection drifts, cylinder pressure drops, combustion goes incomplete. The engine derates, the schedule blows. Cooling water fails. The engine shuts down in minutes. A bearing spikes hot. Days of repair in port. The waste heat turbine craps out. 9% of electrical generation gone with it. Running a power plant where one person watches every gauge, and if any of them go red, the next thing red is your career. There is no roadside assistance in the middle of the North Sea. Mechanical problems get solved on board or the ship doesn't move. Every hour the ship moves, it burns money. About 165 tons of bunker a day at slow steaming speed. Roughly $100,000 worth. A full Asia-Europe round trip burns close to $2.8 million in fuel. And that gets 18,000 containers halfway around the world. Container, the fuel cost works out to roughly $150 to move your phone, your TV, and your office chair from Shanghai to Rotterdam. Less than your Uber to the airport. The cheapest part of anything you own from Asia is the part where it crossed the ocean. The expensive part was the truck that picked it up after it landed. The engineer scans the screens one more time. Everything green. He logs the watch and rotates out. Sometime in the next 24 hours, the part nobody films starts, arriving. Because 9 days of careful sailing comes down to 6 hours of choreography at the other end. And if those 6 hours go wrong, the entire voyage was for nothing. 2 hours out of Gothenburg, a pilot boat appears alongside, matching the ship's 8-knot approach speed. A man in an orange flotation suit grabs a rope ladder hanging off the hull and climbs 30 feet up the side of a moving ship. Maritime pilots have a saying, there are old pilots and there are bold pilots, but there are no old, bold pilots. That man climbing up the side of the ship is a maritime pilot, and he probably knows this channel better than anyone alive. A maritime pilot is a local navigation expert who guides incoming ships through harbor approaches and narrow waters. Years of training on a single port, every tide, current, and shoal between the breakwater and the berth. Once licensed, a pilot might handle 200 approaches per year in that port and nowhere else. Imagine if every airport hired one local pilot who lived there, knew every gust on every runway, and personally stepped onto every incoming 747 for the last 20 minutes of every flight. That is what a maritime pilot does. A pilot mistake on a hull this size is hard to walk back. The Mumbai Maersk, a Triple-E sister, touched bottom outside Bremerhaven on February of 2022 on an inbound maneuver gone wrong. High tidal currents, coordination challenges, a 400-meter hull that didn't handle the way smaller vessels do. What the pilot didn't know on the final 2 minutes of that approach was that the current was already pushing the bow off the line he had locked in. No injuries, no pollution, but 18,000 TEUs sitting on a dredged spoil bank is not what anyone wanted on a Wednesday morning. The pilot gets back on the radio. Tugs reappear from the harbor side. The ship eases into the terminal at under 2 knots. Mooring lines go out. Heavy synthetic ropes, thigh thick, and linesmen on the dock catch them and run them through bollards. Each rope takes tens of tons of static load, and a Triple-E typically uses 12 to 16 of them depending on weather, tide, and port regulations. There are no anchors involved. The whole ship holds in place by ropes. Very, very impressive ropes. Steel arms swing onto position overhead before the lines are even fully tensioned. The first spreader bar locks onto a 40-ton container and lifts the box clean off the stack. It tracks sideways across the dock, drops, and releases. 12 seconds. The next spreader is already on the way down. Those gantries are some of the largest pieces of mobile machinery on the planet. What just lifted that container is an STS, ship-to-shore crane. A giant gantry-mounted machine that picks containers off ships using a spreader bar that locks into the corner castings. A modern STS stands around 90 meters tall, lifts up to 65 tons per move, and completes 30 to 40 moves per hour. A full Triple-E discharge and load uses 6 to 8 of them at once. Picture a Walmart self-checkout where the items weigh 30 tons each and you're scanning them off the side of a building. While the gantries pull boxes off the dockside, new containers stage on shuttle trucks below, and they alternate. Discharge a stack, load a stack, with the lashing crew working behind them, unlocking outbound containers while another team locks down the inbound ones. At the same time, on the seaward side, a fuel barge ties up alongside and pumps bunker fuel into the ship for the next leg. Stores boats deliver food, lube oil, and spare parts. A chief mate on the bridge is already signing off on tomorrow's bay plan. Everything happens at once. The cranes run, below them the lashing crew works the corners. Seaward, the bunker barge pumps fuel. Stores boats roll pallets. The next voyage's bay plan loads on the bridge. And one person's job, the chief mate's, is to make sure none of it collides with any of the rest. A typical Triple-E port stay runs 24 to 36 hours. From the moment the first line is on the bollard, the clock starts. 36 hours. After that, the berth fees go vertical. The next ship is waiting, and the schedule starts losing money. Thousands of containers off, thousands on. Fuel topped up, food restocked, spare parts loaded, lashing rebuilt, voyage plan locked. Then the last crane lifts the final inbound container onto a shuttle, and it's back out again. Bye for now.